First things first, in a problem like this, what's going on? You have the infinite wire over here being the provider of the magnetic field in this situation. If the loop is at the same level as the wire is, you can imagine from a front view, the wire looks like this, and the loop looks like a straight line when we look at them from the front. These circles that make up the magnetic field of the wire, they will intersect right now the actual loop at 90-degree angles. That's what we want to see here. We want to observe that this is actually happening. 90 degrees, all of the field lines of that infinite wire. So why is that important? Well, it just means right now, if you use your right-hand rule, you could determine the magnetic field and how it's going, and not how it's going to hit the actual plane. So in your case, the current is going this way. If we view the situation from this perspective right here, looking back on it, we see the current coming toward our face as it is indicated on this picture here. And the magnetic field, if you use the right-hand rule, it actually will go the other way around. If you use the right-hand rule, it will go again this way. So let's actually draw it. I need to bring this a little closer so that it makes sense what I'm doing. This is the cross section of the plane. You're basically looking at that side right there when I look from the front. And then the magnetic field lines, again, they're perfect circles and they hit that square perpendicularly. As you can see, I'm trying to demonstrate that here. So every single one of those counterclockwise moving lines, they will hit our loop at a 90-degree angle toward this direction, which means we're going to see the magnetic field coming out of the page in the loop. And I will indicate that here. So magnetic field coming out of the page. But hold on a second. The magnetic field of an infinite wire is a popular result in E&M. I doubt that any of you remember it, but it is mu naught I over 2 pi r, where r is the distance from the wire's axis again, I is its current, you know the others are mu naught, and 2 pi are just constants. Okay, so that's the strength. It is definitely dropping with r. So if I'm moving further away in the loop, I expect this to happen here. I expect the magnetic field to just progressively decrease and become like smaller and smaller like this. The same pattern, though, should be happening throughout the wire over here and throughout the loop. I can mimic this pattern by copying and pasting it like this everywhere. So, okay, fair enough. This is the magnetic field situation. Now, if you pay close attention, the loop is also moving. To make things even harder here, the loop is moving this way. Before I get to the motion, though, can you see one sec that if I just left things as they are, there is no change in flux through the loop, because the amount of magnetic field that will be punching through its surface is not changing. So how are we going to get induction? We have to get the flux to change through the loop. Sometimes you have problems that do that by varying the current that's running on this wire here. They make it a time-dependent function. And that definitely changes, again, the flux in here, because this breathes, quote unquote. It breathes like this. If you make the current, for example, a sinusoid, you have this to be breathing. Inhale, exhale, inhale, exhale. And the flux is constantly changing, which constantly induces an electromotive force. But that's not what they do here. They keep the current constant. Okay, that was one scenario. They keep the current constant, which means you're not breathing through the loop. So how are they going to change the flux? Oh, wait a minute. They could move the loop and make it go to a region that has a lower magnetic field if they move it north, for example. So all I'm trying to say here is that these balls over here, you can make them smaller and kind of line them up over here. So they're moving the loop itself to a region of lower magnetic field. And as the loop moves into it, obviously you're going to change the flux. Because now as you move it north, there's less magnetic field over here than you used to have over here. That's what you guys are doing in this problem. So, you move it north at some rate called V. The whole loop gets moved north. How the heck am I going to calculate here the inductance from this? So, the way that we do it, I think I've covered something like this, Neil, with a group last year, but the way that we do it is as follows. You take a line over here along the loop like this. And what you want to do with this line, think about this being a piece of chalk on the board. If I let some time go by, what happens is this line moves north right now. It moves north under the action of this velocity vector. That's what would happen to it. And in the meanwhile, if it was a piece of chalk, it would have smeared this area over here. So this area would have a little bit of width that I would call dy right now. And a little bit of a length, which would be literally the length of the loop. As you can see, that would literally be L right now. So why do I want that? I want to calculate what is the flux that has been received through that little band right now. That little band that you see right now. So I'm basically going to calculate the flux. The flux itself, just like in Gauss's law, how you had the electric field dotted with dA, if you're doing magnetic field, it will be B dotted with dA to calculate the magnetic flux. And, you know, the magnetic field that we're interacting with here is the magnetic field of the wire, the infinite wire here. If they say long wire, they mean infinite. You can take it to be like approximately infinite. Okay, there needs to be some adjustments here about, for example, what the R is going to be. The R is going to be a variable because, as you can see, we're going to be aiming it to come right now and hit the center of this little band that I opened up over here. I need to set up a coordinate system. I choose over here to do this as my x-axis. I don't know, it seems reasonable. And maybe this as my y-axis. Again, it just seems reasonable. I could have very well chosen to do this. It doesn't matter though. At the end of the day, it really doesn't matter. Out of the two options, I think I prefer this one because it will have simpler integration bounds. You will just go from 0 to w when you do the actual integral. But you will pay a different cost. You see, this would be now the R vector leading all the way to the band of interest. But the variable, this variable here, would be your Y. So your R is not just going to be equal to Y. As you can see, it would be equal to S plus Y. That's the only price that you pay there. If you would have moved the x-axis there, the R would have been exactly equal to Y, but then the bounds would have been from 0, sorry, not from 0, from S to W plus S. Either way, you're going to pay a small price here for the adjustment of the axis. I will put it like this, it looks nicer in my eyes. Personal opinion. So, if you're doing the magnetic field right now of the wire, you must realize that at all times it's hitting you perpendicular on the loop, so you don't have to worry about angles or anything like that when you come to the integral. So the B of the wire right now, what adjustments do we need to make here? Well, first of all, the R, we said, is confined to be in the y-axis, and its size is going to be, again, y plus s. Meanwhile, the R vector is, well, we're coming out of the page. I can call that to be just z hat. All right, so this is what the field of the wire became after the adjustments that need to be made for this problem. Now, You walk into the flux. You got to calculate the flux when you're doing inductance. So you take the dot product between, again, magnetic field and dA. Here's my magnetic field that I'm going to be plugging in. Okay. And throughout the term with Jeffrey and Neil, I've been telling you that if you see this type of integral where you have this dot product, you can safely assume that this is just DAZ. What does that mean? That means, again,
George,
yeah? Tell me, Neil.
why is it in the Z direction and not the Y direction?
Well, you see the Y direction is the one going up right now this way, and this is the
Yeah.
X. So this direction should be either negative or plus Z. It's perpendicular to both X and Y right now, the way that
Oh,
we've
that's
set
the
it up.
direction of the magnetic field. Okay,
Yeah,
gotcha.
that's the
Okay.
magnetic field,
No
yeah.
worries.
All good, all good. So this is Z, let's say, over here. All right. So the direction of the magnetic field, cool. We got that. It said you dot it with the A, you get back the element that's basically aligned, has its normal in the Z direction. What is that element? Well, it's this guy, of course, over here. But as you can see, instead of doing just this guy, we have stretched them. This would be DAZ right now. But what we've done instead is we're considering a full rectangle of length L. But why? Let me show you why. So this is a double integral at the end of the day, where you can pull outside all of these constants because they're not getting integrated over. Only the y plus s is getting integrated over. And I want you to see again why we've pulled this outside. So we're doing a little rectangle right now. We said the flux through a little rectangle of size dy by L. In a way, you can bypass the entire integral here. You don't have to integrate anything because I'm not yet there. I want to find the flux, like I said, through this little band. Let's call it d phi b. And I'm going to skip the integral for now. I'm going to be doing, again, my magnetic field through the little area element here. The area element now is referring to the yellow bit. This is dA. Okay, so I'm going to find the flux through that little area that was smeared by the movement of that yellow line north. All right, so if that's the case, when you go over here and you dot the B with the dA, I want you to see that B and dA are mutually perpendicular. How do I know that? Every area has like a normal vector to it. Same with this little band over here that we've created, the yellow band. It has a little bit of a normal to it. This one can be thought of as being out of the page or into the page. I will choose this option because that will make the dA completely aligned with B. I won't have to carry on a negative sign for no reason for the dot product. So the dA right now will literally be in this direction and parallel to the magnetic field. What does that mean? If things are parallel, then I don't have to take any dot products. I literally just take the size of B and the size of the dA. Okay, no integrals, we said. So what is the size of the dA here? Well, we can see what it is from the diagram. It's the width times the length. So I'm going to do here the width once again, which is dy by L. That's how big the dA is. All right, dy by L it is, or L dy if you want. And that describes the little flux right now that we created by moving again the loop north. Okay. Now, I want you to think about this. This was a specific line right now that we took over here that connected one edge of the loop to the other. There are infinite such lines that are moving north at the same time. For example, there's another line over here, okay, like at the bottom part here, let's say, that has also moved north by a little bit, and it has spanned this area as it moved north. There's another line over here that has moved north and has spanned this area. There's a lot of these. And as you can see, the one that we picked is not the only one. So I have to account for the little flux that every single one of these little areas is creating right now as I move the loop north. So I picked one of them in order to cover not just this possibility, but every single possibility of lines that are going to be moved north of this plane. I think you can see where I'm going with this. I have to integrate. Okay, I have to integrate right now the whole thing from the bottom of the loop to the top of the loop, like this. That will give me again the flux that I'm creating. Okay. So you have the little flux over here. That's why this dy is there. And you're going to go ahead and differentiate this. Well, not differentiate, sorry. Integrate this for now. Phi b will then be the integral of this thing. And you're going to do the full extent of the loop here. So the dy is going to vary here from 0 to w to match to get all of the possible lines that are moving north. Okay, so we go over here. All right, we're going to do this. But before I do it, let me think of one last detail here. How do we take care of the velocity? Where does the velocity come in? Because if you do this, you're going to get out a constant, and that's not what I wanted. The velocity comes in when you're doing the change in the magnetic flux. The change in the magnetic flux over here is equal to the EMF. Epsilon induced quite literally is the negative of the magnetic flux with respect to time here differentiated. This is by definition. I think you can see where this is going. If I actually take over here this definition and combine it with what you found over here on the left, you can see where this is going. All I have to do is basically, quote unquote, divide both sides by dt, quote unquote. And this little guy we recognize as the speed. This is the speed that you're moving the lines north. So that's where that speed comes in right now. So that's d phi b dt again over here. Mu naught I v. And there's an L here as well. So v. And then 2 pi y plus s at the bottom. Remember that this is the EMF from one little piece of the entire loop. So this is the magnetic field that we're going to be using. This is epsilon induced from the effect of one single line here. From one single smeared line. That's it. That's all we found here. So wait a minute. If that's only from one line, how do I get the epsilon induced from the entire loop motion? Can anybody take a guess? If that was from a single line that was at position Y at that given moment, how do I get the EMF from the entire loop right now? Shouldn't I take the effect that I just found from the single line, right? And then if that single line was at position Y over here, what would happen if we went over all the positions of Y in the loop? Can you see what I'm going to do here? So I'm going to integrate here. If I want the epsilon induced everywhere, I'm going to integrate from the bottom of the loop to the top of the loop. As you can see, this result. That's going to talk about all the lines, every single line's effect right now. So we're doing here a dy integral at the end of the day. All right. And of course, I can see here how that will evolve. You have mu naught I LV. Everybody here's popping out of that integral except the y over s. The y plus s rather at the bottom. So you're just integrating the y plus s at the bottom from 0 to w. But you know what? That actually is a very popular integral. It's just ln of y plus s.
George.
Yes, Neil.
Mm, so you see, we have that the EMF is equal to the change of flux over the change of time.
Yes.
But then if we were to put an integral on both sides,
Mm-hmm.
right? Because if you integrate one side but the other side, then you would integrate. Wouldn't you be integrating the flux over time, and therefore it wouldn't be a
No, no,
rate of
no.
change?
So I'm not doing an integral with respect to time, first of all. Here, we're going over position. So what you found here, just to understand everyone here correctly what we've done, we have found the effect on the EMF from one infinitesimal portion of the circuit just moving north by a little bit like this. You see? I've moved it north by dy at a certain rate. And we have found what the effect is from that certain motion here of that one single line. But then you go, it's not just a single line that makes up this loop, right? This loop is made out of a lot of these lines, right? One here, right? Lots and lots of these lines are all moving north right now like this and are introducing again the effect of flux here. Every single one of these is moving north. So I want to consider, again, what the entire effect is. If I have the effect of one that sits at a distance y right now from the origin, how can I get the effect, for example, of that one that sits at a different y, right? I have to carry out an integral over the dy range to talk about all of them accumulated together, right? That's what I'm doing here, Neil. It's not a time integral that I'm taking.
Yeah,
Did
no, I understand.
Did the others follow that though? Because this, I picked this because it's the hardest problem on the set. Literally, that's why
I
I'm
think I
going
was
this
just
first.
I think I was just confused because you had a dy earlier, which you got rid of to make velocity, but then you just
Right,
implemented another dy.
right. So I was thinking again here, how to take the derivative of this. So there was two ways of going about it, but one of them is not correct in my mind. One of them was to first integrate the flux through the entire loop, but that doesn't look right to me because if you did that, you would be talking about the total flux and then you would be moving that north. That doesn't look right to me because every single line, like I said here, every single line introduces a new little area here that we have to consider the flux through. It's better to think of it this way. This is something that they call flux linkage, by the way, in EC 106. They call this flux linkage. Maybe it's a term that circulates around in your course. But flux linkage between what and what? Well, your linkage right now is the link between this guy and the EMF that you're going to get. Like the actual element here of this loop, this little element, and how much EMF it's going to be providing you with. That's the flux linkage basically right here. And next, what I do is I integrate over it to get the effect of the entire object. That's what my goal is. So, yeah, weird. Definitely not the easiest problem to start you off with. But once you carry out the integral over the y, you cover all these possible lines that could go north. You get a logarithm out of this, and at the end of the day, your EMF should be looking, if I plug in the bounds, let me see here, mu naught ILV over 2 pi. You plug in the W, you get W plus S minus ln of S. So it should look like ln of W plus S over W, if you put it all together. And that should be the EMF that you generate as you move again the loop north. I want you to see that it's sensitive to the velocity. The higher the velocity, the more rapid the flux change and the higher the EMF. It's also sensitive to dimensions here. Okay, the wider your loop is, the bigger your loop is, the bigger the effect. W plus S dominates over this. So the bigger the dimensions, the bigger this logarithm is. And what else? What else here? I think that's it. That's all I have to comment on. Where did L come from? 1 second. Where did L come from? It was the length of the loop. Okay. Yes. Got it. All right. That's how you would approach a problem like this. Once again, this is entirely motional EMF. The EMF is caused because of motion of a loop in a field. There's also transformer EMF, like I said, where you vary the current so that these vary themselves. Yes, you could have both of them combined together, and these are very, I would say, notorious problems when you do that. Now that I did the hard one, I'm actually going to tone it down and go to a little bit of an easier one, okay? But again, any questions, of course, always let me know. Let me go to the easier one that I have nearby. So, for example, this kind of little guy right here. I think this is more likely to show up than the one we just saw, but you never know because the course is inspired from EC 106. Remember that. So, you have a small 2 mm diameter circular loop with resistance this much at the center of a larger 100 mm diameter circular loop. Both loops lie in the same plane. The current in the outer one changes. Didn't George say something about changing this, causing again this to breathe? That's what's going to happen over here now. You're going to change this current, and these are going to breathe, basically. They're going to actually, they go from positive 1 amp to negative 1 amp. You're actually not just going to breathe, you're going to flip altogether here. That's a big change, right? You're going to flip these vectors altogether when you go to negative 1 amp here. Okay, here's a few things that you got to note about the problem. First thing that should make your eye go a little bit wonky. Why the heck am I assuming that the field is going up? You probably have seen that the field of a loop is more like this, right? So you're probably wondering, what the heck is up with this? I'll tell you. You see, if you were to compare these two loops, how much smaller would you say this one is? Like a little smaller, a lot smaller? What do you think? When you compare the dimensions there, the radius or the diameter. In your opinion, is it a lot smaller, this loop, or a little smaller?
It's a lot smaller.
Right. 50
Yeah.
times smaller, right, in diameter. So, you probably can see where I'm going with this. We're not talking about a loop that's like this, the inner one. You probably can see where I'm going with this. We're talking about a loop that's like this. Maybe even less so. Do you see where I'm going with this? The magnetic field is approximately vertical when it comes to this calculation right now because of the scales. Okay? This is significantly smaller than that loop. So, roughly speaking, the magnetic field going through it is like the magnetic field on the axis of the big one, approximately. Yeah, it works just fine as an approximation. So, we walk over here. That's why you see me again use these guys. And for a ring of current, they make you derive in class what the magnetic field is along the axis. The result, I'm presenting it to you right here. This is the magnetic field along the axis of a circular loop. Loop of current, of course, that is. So it depends on the size of the loop, the current that's running around. This is the position. How far away are you from the center of the loop, right? This is the Z that we're talking about here. Now, obviously, guys, what will be the Z for this green loop right now? Any point on that loop, how far away is it vertically from this guy? What do you think? Is there any point of the green loop that's out here? Or are they all on the XY plane? I don't hear any opinions. Take a guess.
Are they all on the XY plane?
Of course they are, right? So you have over here the z-axis, and maybe you can think of that as the y and x over here. Okay, it's kind of a false 3D diagram. So this is z, this is your y, and this is your x. Yeah, so you can see the green loop is literally entirely on that xy plane. No z for any of its points, which means the magnetic field that it receives always substitutes a 0 for this. Okay, so we can call the radius of the small one here R1 if you want, and the radius of the big one R2. Okay, whose radius goes here, you might be wondering. Well, we're talking about the magnetic field of the big one. Okay, this is the provider. That's the guy's magnetic field. Like, we're considering the big guy's magnetic field. So that's going to be R2 in your subscript here. Okay, the 100 millimeter loop. So it runs some current, which we call I. All right, and again, that's R2 over here. And you can see how it will simplify now. So the magnetic field of, again, the big loop, using the result for loops along the axis, it will be small cancellation here, of course, as you can see. You will get mu naught R2 squared I divided by 2, pi's gone, and then you have R2 squared, square rooted, and then cubed. So I think you can see where this is going.
George, could you just repeat one more time why z is 0?
Right, because we're not interested. Let me make the loop again appropriate dimension here so you can see it's a lot smaller. So
Yeah.
yeah, it's a lot smaller than the blue one. So we're making this 0 because the point that we're going to be integrating the field through, all the points, reside on this green loop right now. And the green loop doesn't have a z component right now. It literally is on the plane of the blue loop. So this distance refers to your point if it was away from the actual xy plane. Because this result has been derived, this is the magnetic field along the axis of a circular loop. And this P was assumed when you did the derivation to be a distance z away from the xy plane here. Like, this was the z. Now, every single one of these p's, follow me here to make sure, every single one of these p's that you're going to do your integral through, look where they are for the green loop.
Yeah, they're all on the z-axis.
The xy plane, rather. Yeah.
Yeah.
So all of them, whenever we're going to do our calculations here in this space, these p's are all going to have no z component. I hope you can see that. That's why I made it 0. So it's adjusting a common result, which you do a lot, by the way, in this course. Adjusting a result to fit the narrative of the problem you're doing right now. Okay.
Right. So how did you know that it was going to be aligned on the z-axis?
The magnetic field, how I knew. Repeat the question, Neo. How did I know if it was aligned? Who was aligned with the z-axis?
The circles were aligned with the z-axis.
Oh, because it says it here. One is contained within the other one over here. They lie on the same plane. Why not let that plane be the xy plane?
Oh,
Right? Right?
okay.
They lie on the same plane. Make them lie on the xy plane and then measure things with respect to z, right? So it's just wisdom, right? You're not going to put it randomly in space. If they lie on the same plane, take a special plane to be that plane. Why not, right? All right. So that being said, you have now an idea of what the magnetic field is. in that center region. In fact, I will get a lot of cancellation here because you've got square canceling with square there, and this is now cubed at the end of the day. But then, once again, look at this. More cancellation. So it looks like your field that's going to be felt by the green loop is this size right now. Just 2R2 on the bottom. That is literally it. Okay, so hear me out. This is the field, roughly, that's going to be felt by your loop. Again, the loop is a lot smaller. We've talked about this. I wanted to make it big, though, so I can fit in some details. I can't make it tiny, tiny. All right, so here we go. You are now calculating again inductance. You have magnetic field, just like you did in the previous problem. Well, what about the flux now? Let's go and get that. To calculate the flux again, all we gotta do is come over here, and I'm gonna make that a little bit bigger. You have the magnetic field again punching through it, okay, like this. All you gotta do is integrate it across its surface. Right there. Integrate that magnetic field through its surface. I know that the current is going to change, by the way. It's a time-dependent current. That's what they said there. Do not worry about that, though, because that's a time dependence, and we're doing a space integral. They don't have anything to do with each other, so it's not like if I integrate right now, I'm going to ruin the problem. This is a time dependence. So, I want to calculate the flux through that little loop over there. How do I do it? Well, the integral of b dot dA. Who's b? The big loop's b. And then you dot that with dA. Who's dA? That's the small loop's dA. So you understand again who is being integrated through what. So the b of the big loop through the dA of the small loop. But you're going to be clever about this. There's a lot of simplifications you can do here. First of all, the magnetic field is entirely in the z direction, and so is the loop itself. Look at the loop itself. It has a normal always pointing up along the magnetic field, which means the dA and the b are both aligned right now, the b of the big loop. Yes, the b of the big loop exists here too, okay? No, I don't care about that region. I only want the flux through the small guy, we said. So I don't care about that fact. I'm going to bound my integral to reflect that. I only want the flux through the green region. And once again, the dA of the small loop, I want you to see that it's parallel with the magnetic field, meaning that this dot product literally goes away, and you just have the b of the big loop and the dA of the small loop multiplying each other, no dot product. So what are these guys? Well, would you believe me if I told you this guy right now does not depend on this at all? Like completely independent of the dimensions of the small loop. You can see the result. I'm not lying. Okay. So this is a constant when it comes to space dependency. It doesn't depend on r, phi, theta, x, y, z. It literally does not depend on space. What does that mean? You can pull it outside of this integral right now, because it doesn't depend on anything that has to do with space. And now you're integrating the area of the small loop? What's the area of a circle?
Pi r squared.
Right, and that r over here is r1, so this entire thing is just going to be pi r1 squared. I think you see where this is going. So you got the flux right there. Wait, it gets more interesting. So you got mu naught pi r1 squared over 2r2, just like that. And then I of t, I will leave it on its own at the front. It's the only thing that depends on time. There's a reason I'm showing it this way. Why? Because the EMF literally is the negative derivative of this. with respect to time. And if everything in front of the current is a constant, it doesn't get differentiated. Rather, the derivative directly hits the current right now. So you end up having minus mu naught pi r1 over 2 r2. Yeah. And then the derivative of the current with respect to time. And it's very easy to find the derivative of the current with respect to time because you were given some info about how the current changes linearly from plus 1 amps to negative 1 amps in 0.1 seconds. You can go over here on the side, put a little plot that represents the current with respect to time, and then you go, oh, you happen to be here in the beginning, and now you're here at the end. And that happened all in like 0.1 seconds. So your current went from being here to being at this location at 0.1 seconds. You can see here how this happened. It happened in the form of a linear decrease like that. All you have to do is find the slope of this. And the slope of that line is the derivative of I with respect to t. Quite literally. So how do you do the slope here? Anybody want to do it for me? What would the slope be?
Will just be a rise over rho.
Right. So yeah.
It's going to be, let's go 0.1 minus 0, I guess, as our top.
So 0.1 minus 0, yeah. And then?
And then it will be negative 1 minus 1.
There you go. So it looks to me, that's going to give you like a negative 2 over 0.1. But you can always simplify that a little bit here. I guess, isn't that negative 20? I think so. So the slope is negative 20 amps per second. That sounds like a derivative to me, right? di dt right here, amps per second. That is literally di dt. So now you know. You put in the fact that this is 20. The dimensions have been given for R1 and R2. Game over. What do you guys think? A few approximations here. I think this is the second hardest problem that you had on there.
George, why is it now that the epsilon induced equals the negative for the change?
The negative is part of something called Lenz's law in physics, and it's there to indicate that the potential is a reactionary potential, meaning that any magnetic field that you're going to make with this is going to be reacting to the change of this flux. It has to go in opposite direction to the change in flux. For example, if you
So why didn't we have that in the other problem?
Didn't we have it here? On the other one here, the negative? Or did I forget it?
Oh yeah, we had it up there.
We
Did
had
we
it,
have
but
it
it
in
took
the?
away, yeah. I'll tell you why. So the
Did
negative
we
is
have it
just
in the when we did the derivative?
right. So the negative here, in short, it's telling you the fact that you are reacting. But when you're looking for the size of epsilon induced, you can imagine that that negative is irrelevant, right?
Yeah.
Right. So here they asked me what is the epsilon induced, right? Or the induced current. Oh, they went a step further. One sec. I didn't cover that one.
I would just
So
be putting it into Ohm's law, no?
exactly. Yes.
Mm.
Did everybody catch that? Veer. Right here, they give you the resistance of the loop, right? So if you want the current, and you know that epsilon induces the potential, then all you have to do is rearrange Ohm's law. And that's also done and done. You have the resistance, they give you the resistance of the loop, and here's the epsilon induced. So long story short, over there, Neo, is that when you put the negative in, it's just to show a reaction. Let me explain. For instance, if you had a loop that was in a magnetic field, but now you're moving it out in a space that there is no magnetic field, guess what? There will be a reaction by the loop itself. It will literally make a current right now to regenerate some of that. It's not going to be as big as what was there originally, but it will literally make a reaction so that it produces this B induced. And why a lot of times that negative is omitted is because you can find out by the use of logic, of course, what is the direction of the current yourself. For example, in this scenario, where you're moving from a field that was larger to one that was smaller, you know that the B induced will reinforce the field. And if you use your right hand rule right now, the one with your curly fingers, you would see that the current must run right now in this direction. So you don't need Lenz's law to tell you. You don't need that negative to tell you what direction you're going to go as the current. You can figure it out from the surroundings. So the negative is just there for being fancy. It's literally nothing more than just telling you to watch out for the magnetic field being reactionary. It doesn't have any meaning in the potential. Also, it can predict what the voltmeter will read, if it will read a -5 versus a +5 volts between two poles on the circuit. But other than that, it's of no use to the current calculation, which is the stuff that you care about. How much current did you generate? What was the size of the EMF? So the polarity of the EMF, yes, it cares about that negative. But all the associated quantities do not. So it's only there to tell you if you're going to read plus or minus 5 volts. You know, that's it. But in the scheme of
Thank you.
things, yeah, in the scheme of things, it doesn't matter. Now, over here, I always include it though, because it's part of the definition. Like when I do EMF, I put it there because it's literally part of the definition. And again, over here at this part, the problem is basically over. You have what the actual potential is. They go for current again. They give you the resistance. You know what to do. Okay. I, according to Ohm's law, is the potential divided by R. So it's just one more move after you find that. And you get the current if you need to find that. Guess what? You could have had a resistor attached to this. Don't be surprised if they put like a resistor over here and they say how much power is dissipated through that resistor. Well, all you have to do there, you know that the power dissipated is V times I. Okay? Where again, you have epsilon induced for V and the I is right there. I think you see where that's going. So you have to be a little careful though. The power dissipated would be V times I. The current is this guy. And the resistor, when you have a wire, compared to a resistor, the resistance is a lot smaller. Like if you were adding here the resistance of a wire and the resistance of a resistor, this is basically going to zero for all we know. Like it's not important as much as this is, right? The resistor is thousands of times more resistive than the wire. So this would be omitted. Okay, and that would be the resistance of the resistor you have on the loop. That's it. So here we just did the wire. There is no resistor attached. But there could have been one, in which case you would ignore that. Because it's too small compared to that. All right. I'll let it be there. That's fine. And I think that's a good point to close the first recording before I crash the computer. All right, 2 inductance problems done and done.